Okay, let's jump into a really fascinating shift in physics today. We're looking at Louis Néel's 1970 Nobel Lecture.
Yeah, it's all about magnetism. Specifically, how we move from thinking it was uh, quite simple and uniform.
To understanding it's actually driven by these really complex local interactions, sometimes atoms basically fighting each other.
Exactly. It's about breaking a major dogma. We need to trace that path, starting with Pierre Weiss and his classical idea.
Right, Weiss. Early 20th century, he was trying to figure out how atomic magnetic moments line up, despite all the thermal jiggling.
So he proposed this idea of an internal magnetic field, an imaginary one, really.
But useful. He said it was proportional to the overall magnetization of the material.
Magneto goals intervalence.
Hmm.
It worked pretty well at first, explained a lot. But there was a catch, a big one.
The assumption, right, that this internal field was perfectly uniform everywhere inside the material.
Precisely. And that assumption had a very specific consequence. If you measured the magnetic susceptibility, how the material responds to a magnetic field, and plotted its reciprocal against temperature,
It had to be a straight line. The math demanded it, based on that uniform field idea.
but experiments weren't always showing that nice straight line, especially above the Curie point.
So, where did the uniform idea really start to fall apart? What broke it?
It came down to the physics getting more granular. Heisenberg, back in 1928, showed that the magnetic forces that matter, the exchange interactions, they're very short range.
So not some big average field across the whole thing, but really just atom to atom, neighbor to neighbor stuff.
Exactly. Think about it like trying to understand a crowd's mood by just asking one person in the center. It doesn't work if people only talk to their immediate neighbors.
Especially in something messy like an alloy, right? Where you have different types of atoms, say A and B, all mixed up randomly. The average field and atom fields would be totally different depending on who its neighbors are.
That's the key insight. And that's what led Néel, around 1932, to propose the concept of local molecular fields. Forget the uniform average. What matters is the field generated by an atom's specific neighbors.
Okay, so how did that change the picture? What was the observable difference?
A big one. Remember that straight line the old theory predicted for reciprocal susceptibility versus temperature?
Yeah.
Néel's local field theory predicted something different, especially for those alloys like platinum cobalt or iron nickel. It predicted a hyperbola.
A curve, not a straight line. And did that match the experiments?
Perfectly.
Hmm.
It explained why the old linear model, the Weiss model, consistently failed for these complex materials. The hyperbolic curve fit the data beautifully.
Okay, so better curve fitting, that's already a win. But you mentioned something even more revolutionary earlier.
Yes. This wasn't just about refining the math for known materials. Néel's theory actually predicted and explained magnetism arising from negative interactions.
Wait, negative? Meaning the neighboring magnetic moments weren't trying to align, they were actively trying to point in opposite directions.
Exactly. Locally fighting, as you put it earlier,
Mhm.
but arranged in such a way that they didn't completely cancel out, leading to a net overall magnetism.
Wow, so a totally different mechanism for being magnetic.
Completely new. Néel called these materials ferrimagnetics. And it wasn't just a theory, it explained real substances like magnetite, text, Fe3 text 04, the classic lodestone.
Magnetite. And I remember seeing those graphs in the lecture, source material magnetite, always had this weird susceptibility curve. It didn't just drop off cleanly.
That's right. There was this noticeable difference between the temperature where the spontaneous magnetism disappeared, the ferromagnetic Curie point fed of it.
And the temperature derived from the high temperature linear part, the paramagnetic Curie point, the ferromagnetic Curie point setup. The curve had this strange dip or shape.
And Néel's local field model, using just one consistent set of interaction coefficients, could reproduce that entire weird shape. It matched both the spontaneous magnetization and that complex susceptibility curve.
That's really convincing. It wasn't just fudging parameters. The same local physics explained multiple experimental facts.
It showed definitively that you couldn't just average everything out. The local details, the specific neighbor interactions, even the negative ones, were crucial.
So the big takeaway seems to be that magnetism got a lot more interesting. We went from a simple picture of uniform alignment to this complex world of local fields, neighbors pushing and pulling.
Which led to entirely new types of magnetic materials, the ferrimagnetics, explained by these sometimes counterintuitive negative interactions.
It really makes you think. If digging into the local short-range physics completely changed our understanding of something like magnetism turning straight lines into curves, revealing new material classes, then maybe it leaves you wondering, how many other things that we describe with simple averages, these uniform models in science or even everyday life, are actually hiding incredibly rich, complex local variations that could unlock totally new insights if we just looked closer.